Hello friends, today I'm going to give a tutorial on how to draw a force diagram. In physics, it's really important to know how to draw a force diagram because Newton's laws stand at the foundation of all of physics. Physics could be described as the study of how forces affect motion. And so we want to be really clear on how to draw force diagrams so that we can set up Newton's laws and begin to analyze how the forces are affecting the motion of things. So let's begin. I'm going to give you an example, a simple example and a complex example. The first example, relatively simple. In the next example, we're going to have forces at angles. So if you want, you can skip ahead to that one. But for now, let's just give the example of somebody like holding a pumpkin. Okay, so first thing you do is draw a sketch. We draw the sketch because we want to get a clear picture of what's happening. Okay, so I'm going to draw a sketch. Here is a person, and they are holding a pumpkin. Say it's got like a green stem on it. Okay, good. Now what? 2, we circle the object of interest. The object of interest here for us is the pumpkin. So I circle that. Again, I'm doing the sketch because I want to notice all of the details. This is a simple example, but if it gets more complicated, you want to be clear. 3, list the objects that are interacting with the object of interest. The object of interest, another name for that, by the way, is the system. Anytime you're doing Newton's laws, drawing force diagrams, you want to be clear, what is the object or the set of objects that I'm analyzing? All right, so what are the objects interacting with the pumpkin? Well, clearly, one object would be the hand that's holding the pumpkin. And then people could say, well, what about the floor? That, the hand's attached to the person's on the floor. Only the objects that are interacting directly with the pumpkin. The floor is not interacting directly with the pumpkin. You could say the person if you wanted, be particular about that. But for now, I'm going to say the hand. And then the other object that's interacting with the pumpkin that we often forget about, unless you've been taught to think about it, is the earth. The earth is pulling down on the pumpkin. Oftentimes people will say gravity. Gravity is not an object. And I emphasize to my students that it's important to think about forces as an interaction between two objects. If we think about forces as, there are types of forces, right? There's, gravity, there are tension forces, there are centripetal forces, lots of different kinds of forces. But we want to be clear about labeling the objects. Otherwise, we tend to throw in kind of imaginary forces. I've seen students just write in FA for like applied force, and there's no object that corresponds to. Also, if you think about forces as interactions between two objects, then it also helps you with Newton's third law to think about this force as the force between the objects, not just this force of what this thing is doing to the other. Okay, so think about forces as an interaction between two objects. Now I've got that's it, right? These are the objects that are making a difference. You could say, oh, well, there's air, there's light, all those kinds of things, but those are minimal. And probably in your physics course, you're not investigating those things. If you are, then you're probably looking at the wrong video. You might want something more advanced. Anyway, moving on to the next one. So now I draw and label a rectangle or a circle. I tend to like drawing a rectangle because that way if I have more than one arrow going up or more than one arrow going down, I'm going from the same level. And then label it. So this is the pumpkin. I don't have enough room to write the whole thing. You can label it like that. Another key thing here is that now when you draw the arrows, the next step, add and label the force arrows. Okay. Force arrows, the convention with the force diagram is that the force arrows always go away from the rectangle or the circle that you drew. The tail connects to either the surface or it connects to the center of the object, but it has to connect, and it has to connect to the tail to the object. Okay, and now I label this. I put a capital F here, and I indicate what the object is. So I'm going to write F, hand. You could write H-O-P, like hand on pumpkin. You could just write H if you wanted. Now I'm going to add the other one, earth. One of the other important things here is that the lengths of the arrows matter. All right. force is a vector, it has direction, but it also has magnitude, and the magnitude is indicated by the length of the force arrow. And so this would be a complete force diagram for this situation of somebody holding a pumpkin. Now let's look at a more challenging example where there are forces or angles involved. So let's take the example of a block sliding down an incline. So something like this. Here's a block, and it's going to be sliding down an incline. And let's say it's a frictionless incline plane. I forgot to write that. Frictionless incline plane. Keep it a little bit simpler for now, just as we're first learning. Okay, so first of all, I want to indicate the direction of the acceleration. Okay, now, so I go here to the sketch, and I indicate that the acceleration is going to be down the incline. Okay. Also, so now when I draw my force diagram over here, what are the objects? Here's the sketch. Already I have that, right? And now the list the objects interacting. That would be the plane and the earth, right? Circle the object of interest, it's that thing. Okay, so now how do I add these? The plane is exerting what we call a normal force. Normal just means perpendicular. It doesn't mean like average or anything like that. Normal is a kind of an old vocabulary word for perpendicular, because a plane surface, when something's resting on a plane surface, always pushes perpendicular to the surface. So I'm going to call this FP for the plane. This is just some block, right? So I'm going to label this block. And then also the earth is pulling down on this block, FE. Okay, so now I indicate the direction of the acceleration. Key thing, when you indicate the direction of the acceleration, don't connect it to the block, to the rectangle or the circle, whatever it is. You draw it off to the side. Okay, same thing if you wanted to indicate the velocity somehow, you draw it off to the side. Only force arrows should be connected to the rectangle or the circle. Okay, now why do I need to do that? I need to do that because if I'm going to use Newton's laws to analyze this, then I have to have everything either perpendicular or parallel to the acceleration. You can't just add up forces that are in different directions and then somehow put them into Newton's second law. In Newton's second law, you have to analyze everything parallel to the acceleration. Those are the things that are affecting the acceleration, and the things that are perpendicular to the acceleration. The things that are perpendicular to the acceleration are not affecting the acceleration. Well, I mean, it could be like a normal force if it's heavier and there's more friction, that kind of thing. But specifically, it's those horizontal forces that are creating the acceleration of the object, the things that are parallel to the acceleration. So what I have to do next is to redraw the force diagram, but I'm going to split up any forces that are not perpendicular or parallel to the acceleration. I'm going to find the components of them that are perpendicular and parallel to the acceleration. So the force of the plane is already good. That is already perpendicular to the direction of the acceleration. There's nothing I have to do with that. But with the force of the earth, this is the original force of the earth. Right. This I have to break up into its components. Okay. Now, parallel to the acceleration is going to be down the incline, so it's going to look like this. And then perpendicular is going to be, parallel to the force of the plane, perpendicular to the plane, like this. Okay. Now, what I like to do, though, is to get these two arrows kind of coming from the same point. Right, so I've got everything connected there to the block in some way. Okay, now how do I resolve this? Well, I have to figure out, these are components of FE, but are they FE cosine of theta or FE sine of theta? I'm going to need some more room there. Okay. Oftentimes I will create another little diagram to do the geometry. Right? It's okay. Think with your pencil. Don't try to just look at it and figure it out. Think with your pencil. Make another little diagram. Do some geometry. And I'm looking at this. Okay, here's theta. So I draw, this is the direction of the the Earth's force, gravitational force. Here is a line that's parallel to the ground. But then if I do this, if I create this splitting up the Earth's force into perpendicular and parallel, I got a little triangle that looks like this. And when I do that, I notice that this little angle here has to be complementary to this angle, but also this angle is complementary to this angle. So two angles that are complementary to the same angle are congruent. Geometry, right? All comes together. And so this angle is theta. If this angle is theta, that means this component is the sine theta times the hypotenuse, which is the Earth's force, and this one is cosine theta. So then I can add that here, right? What did I say? I said that this one is Fe sine theta. I want to give myself even more space still. So Fe sine theta, and this one is Fe cosine theta. And that's it. Now we've created a force diagram, a simple force diagram, and then moving on to how you have to resolve a force diagram into its vectors if the acceleration is not perpendicular or parallel to all of the forces involved. And now from here, I can very quickly and easily write Newton's second laws, Newton's second law for the components that are perpendicular or parallel to the acceleration. So thanks for watching. Don't forget to like and subscribe.